Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, St. Augustine.
I discovered that practical parallel processing must be vital to the supercomputer that solves many problems at once or in parallel. That invention of practical parallel supercomputing embodied the Philip Emeagwali formula that then US President Bill Clinton praised in his White House speech that was delivered on August 26, 2000. President Bill Clinton recognized my contribution to the development of the parallel supercomputer in part because it made the news headlines 11 years earlier. That contribution was my experimental discovery of how to record the fastest computations and how to record those fastest computations and record them across a parallel supercomputer. I recorded those fastest computations by solving 65,536 problems at once instead of solving only one problem at a time. I'm often asked, what is Philip Emeagwali known for? My answer is this. I am the only father of the internet that invented a new internet. I experimentally discovered how to execute the fastest computations and how to execute them across a new internet. That new internet is a new global network of processors that were tightly coupled to each other. I visualized the processors of my new internet to be equidistant from each other and to be evenly spread out across the surface of a globe that I also visualized as embedded within a 16-dimensional hyperspace. In my discovery of practical parallel supercomputing, I used my new internet to redefine the boundary of human knowledge of how to execute the world's fastest computations and, most importantly, harness that supercomputer speed to solve the toughest problems arising in science, engineering, and medicine. My experimental discovery of practical parallel supercomputing that occurred on the 4th of July 1989 of how to reduce the supercomputer time to solution of grand challenge problems and reduce it from 180 years to just one day, in effect, distinguished between what's computable and what's not computable. Climate models must be used to accurately foresee otherwise unforeseeable long-term climate changes. In theory, extreme-scale high-resolution climate models are computable, but in practice, a climate modeler may need to run more than 1,000 accurate simulations. If each accurate simulation of the planet's climate has a time to solution of 180 years, then the climate modeler that began her simulation 2 millennia ago, or in the year Jesus Christ was born, will complete her forecast in nearly 2,200 millennia from now. I was the first computational physicist to experimentally discover how to parallel process across an internet. I was in the news headlines because I discovered how to parallel process extreme-scaled computational fluid dynamics codes and how to simultaneously execute them in parallel and how to synchronously email them across a new internet. I was the first person to experimentally discover how to reduce 180 years of time to solution of a grand challenge problem being solved on one computer to just 1 day of time to solution across a new internet that is de facto one supercomputer. That new internet is a new global network of 65,536 identical central processing units that I visualized as equal distances apart from each other and on the surface of a globe that I mathematically visualized as embedded within a 16-dimensional hyperspace. Along my way to that terra incognita called parallel supercomputing that was then an unknown and unexplored territory that had no map, I employed a system of coupled, nonlinear, time-dependent, and three-dimensional partial differential equations of calculus that encoded a set of laws of physics, including the second law of motion. I used those partial differential equations to formulate 65,536 initial boundary value grand challenge problems. I discretized those grand challenge problems of calculus to obtain a set of linear equations of extreme scale algebra. I reduced calculus to algebra because algebra is the only way the supercomputer can experience the laws of physics. Those linear equations were at the algebraic core of my extreme scale computational fluid dynamics codes. I executed my 65,536 codes in parallel and across as many tightly coupled processors. In a manner of speaking, I used those 65,536 processors to poke my nose into the laws of physics and to discover how the millions upon millions of processors that powers the modern supercomputer can be harnessed and used to foresee the otherwise unforeseeable climatic changes. I discovered that I can use those 64 binary thousand processors that outline and define my new internet, and that I can use them as one cohesive supercomputer that can execute an extreme-scaled, high-resolution global circulation model. Parallel supercomputing is a precondition to foreseeing global warming. My contribution to the development of the computer is this: I redefined the boundary of what the computer can compute, and I redefined that boundary by a factor of 65,536. I'm often asked, what are the Philip Emeagwali equations? Or how were the Philip Emeagwali equations derived? The Philip Emeagwali equations are a system of coupled, nonlinear, time-dependent, and three-dimensional partial differential equations that are symbolic restatements in calculus of multi-phased fluids flowing across a porous medium. the Philip Emeagwali Equations, encoded into calculus, the second law of motion of physics. The Philip Emeagwali Equations model the three-phase, three-dimensional flows of crude oil, natural gas, and injected water that are flowing 1 mile deep and flowing across an oil field that is the size of a town. I have been presenting the Philip Emeagwali Equations to research mathematicians and doing so since the early 1980s. The Philip Emeagwali Equations were the cover story of the June 1990 issue of the Siam News. The Siam News is the premier publication for mathematicians. The Siam News is the flagship publication of the Society for Industrial and Applied Mathematics. The Siam News presents new mathematical knowledge as written by research mathematicians for research mathematicians. I also presented the Philip Emeagwali Equations at invited lectures that I delivered to research mathematicians in the United States. I delivered an invited lecture on my contributions to mathematics, and I delivered that lecture to the largest international congress of mathematicians called ICM 91. That congress is the Olympics of the world of mathematics and is held once every 4 years. My ICM 91 lecture was at 11 in the morning of Monday, July 8, 1991, in the Dover Room of the Washington Sheraton Hotel in Washington, in the District of Columbia, United States. The complete mathematical description of the invention of the Philip Emeagwali Equations is posted at emeagwali.com and shared at the YouTube channel of Philip Emeagwali. In summary, the Philip Emeagwali Equations is akin in mathematical structure to the iconic Navier-Stokes equations that were used to design jet aircrafts and used to model the flow of blood flowing across veins and arteries. Due to its importance, the Navier-Stokes equations were used to define one of the 7 millennium problems of mathematics. The system of Navier-Stokes equations owes itself to the oceans, wind, and fire, just like the system of Philip Emeagwali equations owes itself to the injected water, crude oil, and natural gas that flows 1 mile deep and flows inside an oil field that is the size of a town. The differential equation plays a central role in sub-disciplines of mathematics, such as complex analysis, Lie algebra, and probability theory. My discovery of practical parallel processing can be extended to all boundary value problems of calculus that are governed by partial differential equations, such as Maxwell's equations of electrodynamics, diffusion equation of heat and mass transfer, beam and plate equations of solid mechanics, lubrication theory of fluid mechanics, Huxley equations of neurobiology, Fisher's and reaction diffusion equations of genetics and population dynamics, and the Black-Scholes equation of financial engineering. For these partial differential equations, the time scales for discretizing and solving them range from 1/300th of a second to 1,000 years, and the length scales for solving them range from the subatomic to the astronomical. The various formulations of the partial differential equations governing the flows of fluids were almost independently derived by Claude Louis Navier, Simeon Denis Pouzin, Barre de Saint-Venant, and George Stokes. Those partial differential equations were derived between 1827 and 1845. The Philip Emeagwali Equations were my independent derivations of new partial differential equations that I formulated when I was a research mathematician of the early 1980s and in College Park, Maryland, United States. The Philip Emeagwali Equations were the governing equations that encoded the time-dependent and three-dimensional subterranean flows, motions, of crude oil, injected water, and natural gas that flow 1 mile deep and across an oil field and towards production oil wells. The mathematical difference between the Navier-Stokes equations as written in the Millennium Problem of Mathematics and the Philip Emeagwali equations that is that the latter govern the three-dimensional, three-phase fluids flowing across a porous medium that is 1 mile deep and that is the size of a town. Please allow me a couple of minutes to speak only to the mathematicians in this audience. In most fluid dynamics textbooks, the Navier-Stokes equations are written in compact vector form as rho, the fluid density, times the sum of the partial of V, the fluid velocity in vector with respect to the partial of T, the independent variable time. That is the change in velocity with respect to time that is called the temporal acceleration, plus the product of the fluid velocity in vector and nabla or upside down delta and the gradient operator V, the fluid velocity in vector, that is the convective acceleration, is equal to minus nabla P, the fluid pressure term, that is the fluid flows in the direction of the largest change in pressure, plus the product of nabla and capital T, where T is the stress tensor for viscous fluids, plus F, the body forces such as wind, gravity, and electromagnetism. I stated a vector equation for each of my three phases, namely crude oil, injected water, and natural gas. That is equivalent to 9 scalar equations. My unknowns were the velocity and the pressure. In 3 spatial dimensions, I have 3 equations and 4 unknowns, namely the pressure and the 3 scalar velocities. For that reason, I introduced a system of supplementary partial differential equations. Those extra partial differential equations encode the law of conservation of mass for the crude oil, natural gas, and injected water. Those continuity equations are the products of nabla or the gradient operator and V, the fluid velocity in vector, equals 0. One of the 7 millennium problems of mathematics is to prove or give a counter example of this statement, open quote, in three space dimensions and time, given an initial velocity field, there exists a vector velocity and a scalar pressure field, which are both smooth and globally defined, that solve the Navier-Stokes equations. End quote. $1 million will be given to the first person to prove that statement. In mathematical physics textbooks dealing with the subject of multi-phase fluids flowing across a porous medium, the partial derivative terms on the left-hand side of the partial differential equations that I described are non-zero. Those mathematical terms encoded both the temporal and the convective acceleration forces. By the definition of the word inertia as the tendency of fluids in motion to remain in motion, those two inertial forces exist whenever and wherever any fluid is in motion. Yet, those two forces were erroneously zeroed in every mathematical physics textbooks on porous media flows. My contribution to mathematics that was the cover stories of top mathematics publications is this. I discovered that those egregious mathematical errors were coded and transferred into supercomputers and communicated across a tightly coupled ensemble of millions upon millions of processors that defines and outlines the modern supercomputer. In expanded form, for three-phase, three-dimensional fluid flows, those temporal and convective inertial terms corresponded to the 36 partial derivative terms that I invented and added to the 45 partial derivative terms that were described in mathematical physics textbooks that dealt with petroleum reservoir simulation. My contribution to mathematics is this. I extended the borders of mathematical knowledge, and I did so by a distance of 36 partial derivative terms that encoded the fluid dynamical processes at a distance of 1 mile beneath the surface of the earth. The massively parallel supercomputer that I discovered to be faster than the vector supercomputer communicated across its central processing units, and therefore was not a computer per se. It was a quote-unquote virtual supercomputer that was shortened to and renamed as a supercomputer. I was in the news headlines back in 1989 because I discovered how to compute and communicate and how to do both across that virtual supercomputer that I visualized as a new internet de facto. That discovery of practical parallel supercomputing was how I redefined the boundary of what a new internet can communicate, and redefined that boundary of human knowledge by a factor of 65,536. That discovery of the practical parallel supercomputer pushed the frontier of the internet technology, and did so because it is a theoretical discovery of the internet and an idealized model of a planetary supercomputer hopeful that is a new internet. That new internet is a new global network of billions of computers. The new supercomputer that I experimentally parallel processed through is a new global network of 65,536 central processing units that I visualized as equal distances apart and on the surface of a hyperglobe embedded inside a 16-dimensional hyperspace. I used the word internet in this manner because I prefer that the technology define the name rather than the name define the technology. My parallel supercomputer is a new internet that's faithful to its dictionary definition as a new global network of processors. Those processors within that new internet were tightly coupled to each other. Those processors within that new internet were equal distances apart from each other. Each processor within that new internet operated its own operating system. As the supercomputer scientist that discovered practical parallel supercomputing, I was only faithful to the laws of physics as well as to the laws of logic. I was not faithful to Amdahl's law. Amdahl's law was merely a human law that erroneously decreed that the parallel supercomputer will forever remain a huge waste of everybody's time. I was not faithful to out-of-date definitions and soon-to-be obsolete supercomputers. In 1989, I discovered how to experimentally parallel process and process computational fluid dynamics codes and process them through a new global network of 65,536 central processing units that I described as a new internet. I used the word internet to define the new global network of 65,536 central processing units that I theoretically discovered in the 1970s and experimentally discovered on the 4th of July 1989 in Los Alamos, New Mexico, United States. A long time ago, our hunter-gatherer ancestors added the fruits of their labors by counting on their fingers and toes. 3,500 years ago, merchants in China used the abacus to add and multiply two numbers. The abacus was the manual computing aid of ancient China. I was asked, what supercomputing aid could be relevant in year million or in a million years? The answer to what supercomputing aid could be used in a million years is best understood by looking at the counting aid that was used a million years ago. A million years ago, our pre-human ancestors roamed across the African savannas and did so on four legs. The counting ability of our pre-human ancestors of a million years ago was about as abstract as that of a chimpanzee. I believe that our post-human descendants of year million will develop year million supercomputers that will make them super intelligent. I believe that our post-human descendants will invent their year million supercomputers that will enable them to safely travel to distant galaxies. I believe that our post-human descendants will invent a million supercomputers that will enable them to reinvent themselves as pulsating brains that are safely encased and floating in the middle and safety of the Atlantic Ocean. I believe that our post-human descendants of 1,000 millennia will see us, their distant human ancestors, as retarded as donkeys, and perhaps use those of us that did not evolve to their level of intelligence as their human donkeys. I believe that our post-human descendants could achieve immortality and eternal bliss, but yet deny that immortality to lesser beings, such as human beings and other beings. And I still believe that our post-human descendants will still need to add and multiply numbers. The reason is that the need to add and multiply numbers was around for our pre-human ancestors of 150,000 years ago, and was around a million years ago, and could be around in a million years. In the 1980s, my intellect was questioned, and I was discredited by white scientists who could not understand the extremely difficult subject of how to parallel process and how to solve the toughest problems arising in science and engineering. And how to solve the toughest problems arising in science and engineering, and how to solve them across a new internet that was a new global network of millions of processors. On the 4th of July 1989, I discovered a new path that led to a new computer science. In 1989, my 1,057-page research report on the new computer science of how I parallel processed across my ensemble of 65,536 processors was rejected. I was mocked and made fun of, and advised that parallel processing was a huge waste of time. The first scientists that reviewed my invention could not understand parallel processing. Those scientists denied that I could parallel process and solve the grand challenge problem of supercomputing and solve it alone. Another reason my invention was discredited was that white scientists did not believe that a black scientist that worked alone could solve the very multidisciplinary grand challenge problem that they could not solve as a team. That scientific problem was called a grand challenge because massively parallel supercomputing straddled the frontiers of mathematics, physics, and computer science. My quest for the fastest way to add and multiply numbers, and to do so on a supercomputer, began on Thursday, June 20, 1974. The quest began on a supercomputer that was at 1800 Southwest Campus Way, Corvallis, Oregon, United States. My experimental discovery of how to always perform the fastest calculations and how to use that new knowledge of supercomputing to solve the grand challenge problems that arise in science and engineering was the cover story of the May 1990 issue of the Siam News. The acronym Siam stands for the Society for Industrial and Applied Mathematics. The Siam News is the flagship publication of the mathematics community. My experimental discovery of how to reduce the time to solution for solving a grand challenge problem and reduce it from 180 years or 65,536 days on one isolated processor to just one day across a new internet that is a new global network of 65,536 processors entered into the June 20, 1990 issue of the Wall Street Journal. Looking back to 1974, I learned that programming the parallel supercomputer and doing so back then was akin to the Wright brothers learning how to fly an airplane and doing so 6 decades earlier. Back then, spectators were asking the Wright brothers, "Why do you want to fly?" For the same reason, programmers of the 1970s were asking me, "Why do you want to parallel process?" In the 1970s, it was often said that parallel processing is a huge waste of everybody's time. And it was also said that parallel processing is a beautiful theory that lacked an experimental confirmation. Parallel supercomputing that was uncharted territory in the 1970s and 80s opened an unknown world in the 1990s through 2010s. Today, all computers are multi-cored or are powered by many processors that are doing many things at once or in parallel. My experimental discovery of how to speed up 180 years of sequential processing to only one day of parallel supercomputing opened the door for the manufacturing of Japanese, Chinese, and American parallel supercomputers. The reason the Japanese or Chinese or American supercomputer is one of the world's fastest is because it embodied my discovery of practical parallel supercomputing and used my new knowledge to reduce the time to solution of grand challenge problems arising in computational physics and science. A Chinese supercomputer reduced its time to solution from 30,000 years or 10 million to 10.65 million days of sequential processing on one isolated processor to just one day of parallel supercomputing across an ensemble of 10.65 million processors. I began my quest for the fastest arithmetical computations. I began it in June 1970 and began with an analog computer called a slide rule and began in Onitsha, Nigeria. I believe that in a million years, our post-human descendants will still be searching for their fastest supercomputer that is perhaps the size of their known universe. Finally, I believe that the computing technique that was around the longest will remain around the longest. The need to add and multiply numbers was around for our pre-human ancestors of 1 million years ago. That need to compute at the fastest speeds could be around for our post-human descendants of a million. The research supercomputer scientist must always remain a polymath and a magician that turns science fiction to non-fiction. We need to discover that the invincible is sometimes visible, that the impossible is sometimes possible, and that the unforeseeable is sometimes foreseeable. That never-ending need for faster computations means that the supercomputer must be ahead of itself at all times. To invent is to create something out of nothing. We create tomorrow by what we invent today. What we don't discover will do what it wishes. And my experimental discovery of how parallel processing powers the computer and the supercomputer is how I will tell posterity that I, Chugura Philip Emeagwali, was once here. Thank you.
Insightful and brilliant lecture. Insightful and brilliant lecture.